So good afternoon. Well, in today's lesson, we are going to be looking at input-output methods and devices used for input-output and the organization of the input-output within the computer. In our previous lesson, we learned about computer software. That was in March because really is something we had covered before, and therefore I just perused over it. So input-output is a critical section of the computer, and actually we are talking about the input-output of a computer. We are referring to the subsection of a computer that provides an efficient mode of communication between the central processing unit and the outside environment. Remember when you're talking about the fetch execute cycle, and we mentioned that we have the instruction fetch, we have the decode instruction phase, then we have the part that deals with once we decode the instruction, will it require us to get some data so that the execution is done? So we have the data, fetch data phase, and then after we fetch data, we have the execute phase before we get into the storage phase, and eventually the cycle repeats itself, the fetch execute cycle. So when you're talking of fetch data, where is that data coming from? The data may be derived either from memory, it could be derived from input-output devices. For instance, that data could be derived from a hard disk, that data could be derived from a flash memory, for instance, that data could be derived from keyboard. And the example of the keyboard is a prime example here. Now, programs and data must be entered into computer memory for processing, and results obtained from computation must also be recorded or displayed to the user. That is critical for any computer. Now, among the input-output devices that are commonly found in computer systems are keyboards, display terminal, printers, and disk. Other input and output devices encountered are magnetic tape drives, digital plotters, optical readers, analog to digital converters, and various data acquisition equipment. By the way, what you're calling digital plotters here, digital plotters are what we call big format print, is what we call large format printing. Computers can be used to control various processes such as machine tooling, assembly line procedures, and industrial control. I mean, we know about production line. We have seen assembly lines for cars. You have seen assembly line. You have even seen what happens, for instance, in Coca-Cola companies, where we have the production lines, the way the bottles get the liquid into them, and so on and so forth. Input and output are important modules of computer systems that interface to the system bus. You know now about the system bus, or the central switch, or control one or more peripheral devices. An input-output module is not simply mechanical connectors that wire a device into the system bus. Rather, the input-output module contains some logic for performing a communication function between the peripheral and the bus. And there are reasons why peripherals cannot be connected directly to the system bus. Number one is the fact that they are a wide variety. There are so many peripherals with various methods of operation, and it would be impractical for us to incorporate this logic within the CPU. And we talk of drivers then. The data transfer rate of peripherals is often much lower than that of the memory of the CPU. Therefore, connecting them directly would cause, the CPU to slow down. It would be too much slowed down, wasted cycles, that it is impractical to use high-speed system bus to communicate directly with a peripheral. Peripherals often use different data formats and word lengths than the computer to which they are attached. Actually, there has to be a way of converting that to something compatible to the CPU. It's important to note that the input and output facility of a computer is a function of its intended application. The difference between a small and a large system is partially dependent on the amount of hardware and of course the computer has available the hardware the computer has available for communicating with other devices, and the number of devices connected to the system. And as various models of transfer or architectures will differ, an input-output module is required. It can be said that an input-output module does have some generic functions. And there are two of these. One, to interface to the CPU and memory via the system bus or central switch. And the second one, to interface to one or more peripheral devices by tailored data links. An input-output module is the entity within the computer responsible for control of one or more external devices. And we have seen that, and for the exchange of data between those devices, main memory or the CPU registers. Thus, the input-output module must have an interface to the computer, that is to the CPU or to the main memory, and an interface external to the computer, that is to the external device. We talk of ports, USB, whatever. The major functions or requirements for an input-output module fall into the following categories: control and timing, CPU communication. In other words, the I/O module can do control and timing, can communicate with the CPU, can communicate with the device. It sits in between, is an interface. It can do data buffering. Of course, data that is coming from the external device into the CPU needs to be buffered so that then you don't slow down the communication between the CPU and that kind of a thing. And again, for reasons that some of it had to be converted. So data also that is coming from the CPU going to the device may need to be buffered to synchronize the speeds. Error detection also is one of the functions of the input output module. So when you talk of control and timing, then I've already explained the part to do with CPU communication. There has to the IO connects the external device with the CPU, or what we call the bus, and of course it communicates with the external device. So number 2 and 3 are taken care of. Data buffering, I've explained it, and you know about the data cards. I mean Ethernet cards that you install in the computers, especially the desktops. Gigabit Ethernet, for instance, the amount of buffering needed for that is humongous. Error detection, you've learned about it in the same Ethernet card. There's something about error detection with data transfer. So these are the things you're talking about. And the part that probably we need to know is about control and timing. To coordinate the flow of traffic between the computer's internal resources and those of external devices is what we call control and timing, because of the fact that the CPU will be communicating with multiple devices. Therefore, the internal resources such as the main memory and the system must be shared among a number of activities, including data input and output. During any period of time, the CPU may communicate with one or more external devices in an unpredictable pattern, depending on the program's need for input-output. The internal resources, such as the main memory and the system bus, must be shared among a number of activities, including data input-output. Thus, the input-output function includes a control and timing requirement to coordinate the flow of traffic between internal and external devices. For example, the control of the transfer of data from an external device to the CPU might involve the following sequence of steps. The CPU interrogates the input-output module to check the status of the attached device. The input-output module returns the device status. If the device is operational and ready to transmit, the CPU requests the transfer of data by means of a command to the input-output module. The input-output module obtains a unit of data, that is for instance 8 or 16 bit, from the external device. The data are transferred from the input-output module to the CPU. If the system employs a bus, then each of the interaction between the CPU and the input-output module involves one or more bus administration. The preceding simplified scenario also illustrates that the input-output module must have the capacity to engage in communication with the CPU and with the external device. CPU communication involves 1. Report with a status signal. Common status signals could be busy and ready. There are also signals to report various error conditions. Address recognition. Just as each word of memory has an address, so does each input-output device. In other words, each input-output device has an address. Thus, an input-output module must recognize one unique address for each peripheral it controls. On the other side, the input-output module must be able to perform device communication, and this communication involves commands, status, information, and the data. An essential task of the input-output module is data buffering. The need for this function is apparent, and like I had explained, the gigabit Ethernet, we know about the keyboard, all these have some buffer which is there to facilitate the functioning of the input-output module. The input-output module accepts commands from the CPU, yes, and these commands are generally sent as signals to on the control bus. For example, an input-output module for a disk drive might accept the following command: read sector, write sector, seek track number, and scan record ID. The later two commands each include a parameter that is sent on the data bus, used for the exchange of data between the CPU and the input-output module. Data coming from main memory are sent to an input-output module in rapid burst. The data are buffered in the input-output module and then sent to the peripheral device at its data rate. This is what we call for communication between the internal and the external. The buffering becomes important to synchronize the speed. In the opposite direction, data are buffered so as not to tie up the memory in a slow transfer operation. I had explained that earlier on. The generic model of input-output module is shown here. We have the address line, you have data lines, you have control lines, you have the input-output module, you have links to the peripheral devices, and you have the system bus. Sometimes we call this a port, the links to the peripheral devices, the USB port. And due to the differences in the transfer rates between the peripheral and the CPU, the I/O module reports on its status. For example, if an I/O module is asked to send data to the CPU, that is read, it may not be ready to do so because it is still working on a previous I/O command. Buffering also works to eliminate the delays due to different transfer rates. Now, CPU communication. I just talked about this communication between the CPU and the external device, and communication between the I/O and the CPU, the CPU and the and the external device. Data buffering, we've just seen that. Error detection, for instance, when there is a paper jam in a printer, bad disk track, transmission error, and so on. These errors are reported using some error status reporting codes to the I/O and eventually to the CPU. Now, how do we access the I/O devices? Most modern computers will use a single bus arrangement as shown below. So we have this, sometimes we call it single bus structure in the system bus. We have processor, memory, I/O device 1, I/O device 2, 3, up to n. The processor, memory, and the I/O devices are connected on this bus, which consists of 3 sets of lines as discussed before. You know, those 3 sets of lines, I hope you understand. What you're calling a bus here has these 3 sets of lines: address line, data lines, and control lines. All of them in one. Well, they're separate, but they're bounded into one physical gadget. When the processor places a particular address in the address line, the device that recognizes this address responds to the commands issued on the control lines. The processor requests either a read or write operation, and the request data is then transferred over the data lines. When I/O devices and memory share the same address, if you have an I/O device here that shares the same address as a memory, then we say that that device, that kind of arrangement, we call it memory mapped I/O. I think you have ever heard of that, memory mapped I/O. And with memory mapped I/O, any device instruction that can access memory can be used to transfer data to or from a input-output device. For example, if data is the address of input buffer associated with the keyboard, the instruction move data to register O reads the data from data and stores it in the processor register RO. Similarly, the instruction RO data out, data in, we read, okay, data out sets the contents of register RO to location data out, which may be the output data buffer of a monitor or a printer. Now, well, let me explain something here. This is the instruction. I think we came across this earlier on, and now you know how to read this instruction. Ideally, we should read it from this end, RO to data in. That's how it works. But for reasons of this part section of the notes, data in gets into RO. But take note, and this is important, from assembly language, Microsoft assembly language, then we read it the other way around. I mean the Intel processor, we read it the other way around. The data in into RO, data out into RO, something of the sort. In other words, this ought to be here and this they ought to be swapped. But that's not a major thing. Just read the notes to understand the concept. In another type of organization called input-output mapped, the memory excuse me, and the input-output address spaces are separate. In this case, the CPU must execute separate input-output instruction to activate either the input-output or write I/O lines, which cause a word to be transferred between the address I/O and the CPU. Sorry for that. I think I live close to an airstrip, so these things sometimes happen. Now, we are going to have a look at some input-output techniques. We have already mentioned about memory mapped. I want us to look at there are 3 types of input-output techniques being followed, which have their own advantages and disadvantages. The 3 of them are programmed I/O, interrupt-driven I/O, direct memory access. In programmed I/O, and interrupt-driven I/O, especially for when you talk of programmed I/O, both the input-output and the CPU have a register, so it's like they are working in a separate devices, and the CPU could keep on waiting for the I/O to return. Well, and that is the reason why we go for the interrupt-driven I/O, where now in interrupt-driven, as you're going to see, the CPU issues the signal to the input-output, and the input-output gives an interrupt. so that you can use the bus to transfer the data, or to when it is ready to transfer the data to the CPU. That interrupt means the CPU stops functioning in order for it to process what is incoming. That temporary halting of the operation causes what we call a context switch. In other words, whatever the CPU was doing has to be held, and has to be, after the interrupt is over, has to actually to be returned to the same place it was. This is time consuming. In direct memory access, what happens is that the CPU surrenders control to a DMA module. It's actually a hardware. It's actually an assistant to the CPU. So this DMA module picks up the responsibility of the CPU and manages the transfer of data from the input-output module into the CPU through the bus. When this is happening, the CPU is actually continuing with the processing. Now, how do we avoid the interrupt? So what the direct memory access or DMA module does is it waits for the fetch execute cycle and the delays therein. For instance, during the fetch cycle, there is a delay because there is a delay when the instruction is being fetched. There is a slight delay before that instruction gets to the instruction register, and there is also a delay, or the program counter, whichever the case. There is also a delay between the time that the instruction is decoded or the data is being fetched for the instruction to be executed. There is also a delay after execution when the data is being saved or stored. When this is happening, the DMA gets quick control of the bus, transfers the data to where it's needed, and leaves just before the CPU takes back the bus. In this way, there is no interrupt issued. In this way, the input-output module function without interrupting the CPU. We call this cycle stealing. You can Google cycle stealing and you see. Basically, this is what is explained in this other section, and I think I've tried to simplify it for you, but you can have a quick look. Excuse me. With programmed I/O, data are exchanged between the CPU and the input-output module. The CPU executes a program that gives it direct control of the input-output operation, including sensing device status, setting a read or write command, and transferring the data. So the CPU has full control. The following steps are followed through an operation by the CPU. CPU requests for input-output operation. Input-output module performs operation. Input-output module sets status bit. CPU checks the status bit periodically. Input-output module does not inform CPU directly. Input-output module does not interrupt CPU. CPU may wait or come back later. The procedural presentation of the programmed I/O is as follows, as you can see in this diagram. So this is what you're saying. I think I need to make this lesser so that it can be visible in its entirety. Zoom out. I think you can see the entire of it now in the programmed I/O flowchart. So in programmed I/O, what happens? CPU asserts read command to input-output. CPU reads status of input-output. So you can see status of input-output. Yes. Is it ready? Is the input-output ready? Not ready? CPU reads the status. Ready? Is there an error codation? Report error codation. Ready? CPU, if it's ready, if the I/O is ready, CPU reads a word from the input-output module, and it writes one word to input-output module. If it wants the input-output module to transfer that to the memory, then the transfer is complete. And that's how the I/O module works in programmed I/O. This method wastes CPU time because it has to wait for I/O module to complete the operation for it to continue processing. Programmed I/O is most useful in small, low-speed systems where hardware costs must be minimized. Programmed I/O requires that all I/O operations be executed under the direct control of the CPU. That's why we are saying it is wasteful. In other words, every data transfer operation involving an input-output device requires the execution of an instruction by the CPU. Typically, the transfer is between two programmable registers. One, a CPU register, I had mentioned that earlier on, and the other attached to the I/O. There is a delay, whichever way you look at it. Now, interrupt-driven I/O. The problem with programmed I/O is that the CPU has to wait a long time for the I/O module, either in the case of transmission or reception of data. The CPU, while waiting, must repeatedly interrogate the status of the I/O module, as you have seen in that diagram. As a result, the level of performance of the entire system is severely degraded. So what is the alternative? An alternative is for the CPU to issue an I/O command to a module and then goes on to do some other useful work. The I/O module will then interrupt the CPU to request service when it is ready. In other words, if, for instance, you have X, which is the CPU, and Y, which is the input-output module, instead of X, the CPU, keeping on polling or checking whether Y is ready, X issues an instruction to Y, go and do this task. When Y is done with the task, Y tells X, I'm ready with the task. Are you ready to consume what I have, the report? And the CPU just gets that interrupt, consumes the task, and does the processing. The deal is done. That is much easier, as opposed to where I give you a task and then I keep checking whether you are done, you are done. I should give you a task like the way I give you an assignment. You go complete. Once you're complete, if you have agreed on a certain date, on that date you tell me, Mwalimu, here are the answer sheets. Go and mark. That is much easier. But if I give you a task and I don't give you a deadline, you keep on asking, and I keep on asking you, are you through? Are you done? Some of you will finish next year, for obvious reasons. So it is much easier to manage it the other way. Let the I/O module interrupt the CPU to inform me that it is done. That way the CPU can continue functioning as it waits for the interrupt from the I/O. It saves a lot of time. However, in the process, the CPU has to save the context as it handles the interrupt. Here you are. Let's see. So CPU asserts read command to I/O. It reads the status of I/O module, checks the status. If it's ready, CPU reads a word from I/O module, or CPU writes a word to the I/O module, and then the transfer is complete. It is the I/O module that will poke the CPU if things are not working, or if things have worked to completion. So either reporting an error or reporting that the task has been done successfully. But now that is not enough, because even the interrupt is difficult. We look at a way in which the CPU can continue operating continuously without being interrupted, because we want it to be at its best, optimal performance. So here is where we need the direct memory access. Interrupt-driven I/O, though more efficient than simple programmed I/O, still requires the active intervention of the CPU to transfer data between memory and an input-output module. And then data transfer must traverse a path through the CPU. Thus, both these forms of I/O suffer from two inherent drawbacks. One is that the I/O transfer rate is limited by the speed with which the CPU can test and service a device. The CPU is tied up in managing an I/O transfer. A number of instructions must be executed for each I/O transfer. You know, that kind of interrupt handling by itself. There is somewhat a trade-off between these two drawbacks. Consider the transfer of a block of data. Using simple programmed I/O, the CPU is dedicated to the task of the input-output and move data at a rather higher rate, at the cost of doing something else. Interrupt I/O frees up the CPU to some extent, at the expense of the I/O activity and I/O transfer rate. When large volumes of data are to be moved, a more efficient technique is required, such as the direct memory access. In direct memory access, we have an additional module on the system bus. The DMA module is capable of mimicking the CPU and indeed of taking over control of the system from the CPU. The technique works as follows. When the CPU wishes to read or write a block of data, it issues a command to the direct memory access module by sending to the direct memory access module the following information: whether a read or write is requested, the address of the I/O device involved, the starting location in memory to read from or write to, and the number of words to be read or written. The CPU then continues with other works. It has delegated this I/O operation to the DMA, and that module doesn't disappoint. It will take care of it. The DMA module transfers the entire block of data, one word at a time, directly to or from memory, without going through the CPU. When the transfer is complete, the DMA module sends an interrupt signal to the CPU that the CPU is involved only at the beginning and at the end of the transfer. That is wonderful. The DMA module needs to take control of the bus in order to transfer data to and from memory, for sure, because it is transferring using that bus. For this purpose, the DMA module must use the bus only when the CPU does not need it, or it must force the CPU to temporarily suspend operation, what we call an interrupt. The latter technique is more common and is referred to as cycle stealing. since the DMA module is in fact to use a bus cycle. I mentioned about that earlier on. The CPU is suspended just before it needs to use the bus. The DMA module then transfers one word and returns control to the CPU. Note that this is not an interrupt. The CPU does not save a context and do something else. Rather, the CPU pauses for one bus cycle. The overall effect is to cause the CPU to execute more slowly. Yes, it does execute more slowly, but with no interrupt, it is faster. So the DMO is more efficient than both the other two techniques. The concept of cycle stealing is explained here in this diagram. I said it can take the processor the fetch cycle. It can steal the cycle at this point because fetch cycle takes some time before the instruction is fetched. It also takes some time after decoding to fetch the operand. That time it can also exploit. It can also exploit the time where after executing the instruction, the resource has to be stored. These are areas where the DMA can steal the cycle. Now interrupts. Well, I think we had covered interrupts when we were discussing about the fetch execute cycle. An interrupt is a synchronous event that suspends the CPU from its ordinary operation and quickly jumps to pre-programmed routine called a handler. The CPU must be able to return to its original operation after executing the service routine. That concept of a program interrupt is used to handle a variety of problems that arise out of normal program sequence. Program interrupts refers to the transfer of program control from a current running program to another service program as a result of an externally or internally generated request. Control returns to the original program as the service program is executed. The interrupt procedure is a principle similar to the subroutine call, except for three variations. One, that the interrupt is initiated by an external or internal signal rather than from the execution of an instruction, or so to say, a program. The address of the service program that processes the interrupt request is determined by a hardware procedure rather than from the address field of an instruction. You can replace instruction here with a program. Excuse me. In response to an interrupt, it is necessary to store all the information that defines the state of the computer rather than storing only the program counter. We call it the context switch. So after the computer has been interrupted and the corresponding service program has been executed, the computer must return exactly to the same state. We said before the interrupt. It's called context switching. And that context switching involves program status word, that is the saving of all the status bits in what we call the program status word, so that it can be they can be restored to the original form, and therefore we say that the context has been restored. And that's it. This is this just explains the concept of the interrupts. Now we know that when you're talking about I/O, we have three ways of organizing the I/O. One is programmed I/O, the other one is interrupt driven and direct memory access. And you should be in a position now to explain why the interrupt driven I/O is more efficient than the programmed I/O, and why the direct memory access DMA module technique of input output is more efficient than either interrupt driven or programmed I/O. And of course, within that explanation, you should be able also to explain the idea of cycle stealing. Thank you. We meet in the next lesson.